Hi everyone, in this video we'll be discussing on the real-life example chosen for the KIB2003 Mechanics of Material assignment, whereby it relates back to the application in the Mechanics of Material cases, focusing on the Biomedical Engineering application in the medicine field, specifically in the orthopedic field, which is the hip implant. The group 5 members, which are Arvind, me myself, Jilin Wong, Vinod and Shishmita, have analysed the learning outcomes of the case study and discussed on improvement that could have been done from the perspective of mechanics of material, which will be discussed in this video later. Without further ado, let us discuss on the outcome of the study. In this video, we'll be focusing on the objective of the discussion, followed by the introduction to the hip implant. Next, we'll be focusing on the working principle of a hip implant. Besides that, we also will be covering on the manufacturing of the hip implant. Most importantly, we'll be covering on the mechanics of material application, whereby we'll be looking through all the learning outcomes which will be discussed in depth in this video. Next, we'll be discussing on the application in hip implant, whereby we'll be discussing on the improvements that could have been done to the hip implant itself. Last but not least, we'll be summarizing all the outcomes of the discussion in the conclusion later. Now, what are the objectives that we have discussed? The objective of this assignment covers strong to demonstrate the mechanics of materials learning outcome using a real-life example, which was the hip implant. The learning outcomes could be further divided into 4 different parts, which are the learning outcome 1, which is to solve problems involving hip implant under the action of axial and torsional load. The second learning outcome will be covered, which is to solve problems involving stress in beams of the hip implant. The third learning outcome covered is the stress evaluated and deformation of the hip implant due to the compound load. And finally, the fourth learning outcome is to present ideas on the mechanics of material applied in the hip implant itself. The real-life example chosen, which was the hip implant, will be analyzed in depth throughout the video. Now, let's take a look.
I'm Vinod and I'll be explaining on the introduction part. Now let's go to the working principles. The hip joint basically substitutes the already present hip joint that is natural anatomy of our body to mimic the similar functions as close as possible. The surgically installed hip implant usually articulates with the femur to the acetabulum, the same way as the hip joint is also known as the acetabular femoral joint. Thus, the bone implant carries out function to connect the lower extremities of body to the axial skeleton. This hip implant allows movement in all 3 major axes, where the center point of the axis is the femoral head and the 3 axes being the transverse axis, longitudinal axis and sagittal axis. The transverse axis allows flexion and extension movement of the thigh to the hips to be done. Meanwhile, the longitudinal axis permits thigh to move vertically for internal and external rotations to be carried out. Contrary to the first 2 axes, the sagittal axis concerns the forward and backward movement, allowing abduction and adduction to be performed. In addition to this, acetabulum also functions in weight bearing and maintaining stability. What we can narrow down from this is the usage of different techniques to build the hip implant, which are CATIA V6 mimic software ANSYS R19. CATIA V6 is usually used in building the human femur, while as ANSYS R19 is basically used for static structural analysis. When discussing about manufacturing, it is necessary to take account of popular types of hip implant. First being metal on polyethylene, M on PE hip implant. The bearing is highly popular, and what is so attractive about this type of bearing is its safe, predictable and cost-effective bearing aspect. Unfortunately, the M on PE does not come with its issues such as implant failure due to PE debris, which releases perioprosthetic osteolysis through the secretion of proteolytic enzyme and cytokinesis. This is why some surgeons opt to use metal-on-metal hip implant or metal-on-metal hip acetabular head, which is understood from its name. It consists of a metal ball component with a metal socket, though in the past there had been some issues revolving metallolysis. Next, let's look at the ceramic on ceramic for ball and socket articulation. C on C is highly suitable in younger patients due to its hardness and less wearing properties. The cons of this implant occurs when there is a fracture formation, which devastatingly results in third body wear. Thus, in order to reduce the current errors in design and manufacturing, new methods as introducing pits or doing surface texturing can be done. Hence, for traditional methods such as drilling, milling and grinding are less opted, and can be replaced using an electrical discharge machine (EDM) or even through a computer numerical controlled electric discharge machine, which is claimed to increase the precision in making hip implant and removes electrical conductive materials. The electric conductive materials are removed into their targeted shape. This is made possible through spark formation that is based on thermoelectric between the electrode and the workpiece. What is so appealing about the process is that we are able to remove chatter, mechanical stress, and also reduce vibration during manufacturing to create a hip implant with better dimension accuracy and higher quality surface finishing. Now to the next presenter.
Good day everyone, I'm Alvin and today I'll be explaining the second part, beginning with the past of total hip arthroplasty. So, total hip arthroplasty, also known as total hip replacement, can be identified as one of the most successful orthopedics inventions. So, beginning in 1891, Themistocles Gluck, a German physician, attempted hip replacement procedures by using ivory implants to replace the femoral heads of the patients where the hip joints had been destroyed by tuberculosis. And later in the end of 19th and early of the 20th century, surgeons experimented on interpositional arthroplasty involving placing various tissues such as fascia lata, skin, and even thick bladders of mucosa between articulating hip surfaces of the arthritic hip. This was actually presumed as a way to smooth out the deteriorating articular hip surfaces. So later in 1925, the first arthroplasty mold from hollowed out hemisphere glass was made, which could be placed over the femoral head. But this indeed was to provide a smooth surface for movement. But then, although glass has been considered as a compatible material, it shattered as it was unable to withstand large amount of force being distributed towards the hip joint. So later, the similar surgeon, along with Philip Wise, experimented with stainless steel to create the first total hip replacement that was fitted to bones with bolts and screws. So next would be in 1940, there was a first metallic hip replacement performed. So this design consisted of the proximal femoral prosthesis, about 12 inch long, with a large head made out of metallurg and attached with bolts and at the end of the femoral shaft, leading to an early form of hemi-arthroplasty or partial hip replacement. So this design actually gained popularity and eventually developed into an improved version, which is still in use currently, inserted within the medullary canal of the femur, where bone growth results in its more permanent attachment. Then in 1953, the usage of metal-on-metal prosthesis on a regular basis was introduced, and the usage of cemented hemi-arthroplasty for neck of femur fracture treatment with a new one-piece cobalt chrome socket as the new acetabulum was carried out. So the survival rate was high, actually around 74%. However, the usage of this prosthesis was declined due to certain local effects of metal particles, which was seen during revision surgery, which actually is a prosthetic failure. So in early 1960s, the hip replacement consisting of three components, which are the stainless steel femoral head, polyethylene acetabulum socket, as well as acrylic bone cement, was developed, and it is considered to be low friction arthroplasty, as the usage of small femoral head reduces wear due to its smaller surface area. So beginning with the next part, which is the evolution of hip implant. It began with treating degenerative hips with tissue interpositional arthroplasty using materials such as fascia lata and thick bladder. So using glass molds in 1937. So this was actually the first attempt of total hip replacement, and then unfortunately this was considered as a failure due to unsatisfactory results, and in the 1960s, low friction arthroplasty was the very first successful attempt using acrylic cement for fixation. So in this method, the medullary canal is actually removed from the cancellous bone, and a thin cement mantle serves mostly as a wide filler to implant a canal filling femoral component or line-to-line fit. And then followed by the taper slip and composite rim concepts were gradually refined in cemented stem designs. So modern cementing procedures were created with the use of pulsative lavage, retrograde, femoral canal cement drilling, and cement crystallization. So next would be the early uncemented implant designs created for osteolysis, but actually of extreme stiffness, having cylindrical shape and chrome cobalt alloy, which led to diaphyseal fixation from extensive coating. So as a result of stress shielding, actually a significant rate of mid-thigh discomfort and proximal bone loss was found. So stem designs became more flexible with a non-cylindrical form and titanium-based alloy. Most of them are partly coated for improved proximal fixation and load transfer. This was actually also to prevent intraoperative femoral interversion correction. And then the first generation of uncemented cups failed due to excessive micromotion between the liner and the metal back because of a defective locking mechanism design. A large quantity of polyethylene debris was produced, leading to osteolysis and septic loosening. So a coat of hydroceptide was applied to the segmentless cup to improve bone ingrowth and accelerate closure of the bony gap. Last but not least would be the first generation of UHM-WPE, which is ultra-high molecular weight polyethylene, was susceptible to volumetric wear due to its low abrasive wear resistance. The resulting debris triggered a macrophaging reaction in the periphrosthetic tissue as well as bone reabsorption by activated osteoblasts. Alternative bearings used ceramic, metallic, or ceramerized metal alloy. Low wear, highly cross-linked polyethylene has been used as well. So this was a glimpse into the past of the evolution as well as the past of KIB implant. Thank you.
Hello, my name is Jillian Wong and I will be presenting on the mechanics of material application for our assignment. First, the free body diagram of the hip implant is drawn. We identify the X', Y', Z' as the axis of the femur implant-based system. These are the information that we can get from the hip implant and the formula that we will be using for the assignment. So by assuming the average human weight to be 70 kg, which also assuming abductor muscle to be 600 Newton, we can calculate the peak axial force Fz equals to 228.9 Newton. Next, for the resultant force, the formula used are R squared equals to Fm squared plus Wt squared minus 2 Fm Wt cos 135 degree, which is 45 degree plus 90 degree. The resultant force will be 778.86 Newton. Next, to substitute the value of R and Fz into the equation, we can get the peak shear force V equals to 744.46 Newton. Next, we will need to calculate the bending moment, which is V multiplied with N. So, peak bending moment equals to 22.33 Newton meter. Next, to calculate the peak compressive stress sigma at a point C, we find the R equals to half of diameter of the head, which is 28 millimeters. Converting it to the SI unit, which is meter, we get R equals to 0.014 meter. Next, substitute the values into the equation. Sigma equals to Fz over pi R squared plus V multiply N multiply R divided by pi of 4 bracket R to the power of 4. Sigma equals to 10.78 megapascal. Next, we need to evaluate the stress and deformation of the device due to compound load. The strain equation, which is equals to M over ZE. We know that the material used is titanium alloy. The Young modulus equals to 120 gigapascal. Shear modulus 45 gigapascal. Stem length equals to 130 millimeters. Distal tip diameter is 7.4 millimeters. Substituting the value, we can calculate strain equals to 9.349. That's all from me. Thank you.
My name is Sushmita and I'll be talking about the mechanics of material application in hip implant. So this is a femur bone. So you can see there is three types of force which acts on the femur, which is Fx, Fy and Fz. So Fx actually represents the force on the knee axis, while Fy represents the working direction and Fz represents the force on the knee axis. So Fz is considered the load of the human body, which is the weight of the body. and R is the resultant force. So in a normal hip joint, the force is actually distributed to the cancellous bone in femur, and then the force is transferred from the cancellous bone to femoral head, and then from there it transfers to the femoral shaft, and that acts as a beam which is affected by both compression and bending forces. In a hip implant, the force actually acts on the implant first, so it actually removes all the stress which is on the bone, and this causes stress shielding. What is stress shielding? Stress shielding is when the bone doesn't get the stress which it normally gets. That means normally you see the force is distributed straight to the cancellous bone, but now it's distributed to the implant rather than the cancellous bone. So because of this, the bone doesn't have stimulus to have continued remodeling, restructuring of the bone. That means to withstand any pressure, and this will cause the bone to become more porous and less dense. After the implant, then only the force is transferred to the cancellous bone and followed by the femoral head and femoral shaft. So mechanics of material in hip implant, you can see three, which is the stress and strain, load and deformation. So you can see shear stress in between the prosthetic stem and bone, and stress and strain produced is actually the load of the human body. So you can see three types of loading, which is axial, bending and shearing load. Axial load is considered as compressive force, and in the femur it is actually called shear force. So bending stress occurs when it's affected by the movement arm of the stem and bone. That means stem and bone, meaning it is the implant inside the femur, and that part of the implant you can see bending stress at the two ends of the implant. So deformation actually happens when the stress and strain increases beyond yield point. So what will happen is, at a certain point, there are possibilities that the material can deform because of the increased stress and strain. So materials used should have high elastic modulus to withstand this stress and strain. When you have high elastic modulus, the stiffness increases, and this will reduce deformation from happening. So this is the distribution of stress on the hip implant. So the compression strain happens on the medial side, while the tensile strain happens on the lateral side. Bending stress occurs and reduces to zero at distal end of the stem of hip implant. So radial stress is affected at two ends of the bone, where bone and stem is in contact. That means if this is the femur, the implant is inside, so these two ends is where radial stress is formed. So from here we can realize when the stem is shorter, you get larger radial stress, and when the stem has a smaller movement arm than the femur, the stem has an increased amount of stress compared to the bone. And adding to that point, when the stress is increased amount of stress is at the stem compared to the bone, this will cause the bone to have reduced amount of stress, thus it will cause the bone to get more porous and less dense and weaker to withstand the whole body weight. So these are the improvements of hip implant, which is the steep growth. So these are the steep growth, which is the stair-like design at the implant, and this stair-like design of the implant causes even distribution and smooth transition of stress. And these stair-like implants, because you want the bone and the implant to have equal amount of stress, so that stress shielding doesn't happen. Apart from the steep growths, we would like to add fillet radius, which is two sides which are curved. That means it will have gradual transfer of stress rather than sudden distribution. And the length of the stem, which is the implant, should be long to reduce radial stress on the implant, and the movement arm should increase to reduce bending stress, so that the implant doesn't undergo a deformation and it will last long. I think that is all from me. Thank you.
Hi, it's me Veer again, and I'll be explaining on the conclusion. So before we head to the content, here's a quote from Steve Jobs which goes as, "Innovation is the ability to see change as an opportunity, not as a threat." So the Skyler Secure Fit Advanced Hip Stem, which is the one that our group chose as real-life biomedical engineering case, is intended for cementless press fit application. The proximal region of the stem is coated with pure Flix HA over conventionally pure titanium plasma spray substrate. Though it is far from being completely sustainable and fully perfect, the Skyler model of hip implant is the best in the market currently, hence being the best seller worldwide. With the technical possibilities currently offered by materials and prosthesis engineering, the need to consider individual variation in hip anatomy is gaining recognition among orthopedic community. There are more and more technique solutions to suit all femoral acetibular shapes. In parallel, the recent understanding of hip biomechanics with regard to dynamic relationship between the femur and acetabulum has altered our classical view of anatomy in these regions. These concepts present a challenge for each orthopedic surgeon and also biomedical engineers, and should be the central point in our future upcoming research regarding hip implant. So before we end, here is our group mates, Arvind Pillai, Darshivini, Jillian, Sushmita and Lee Vinod. That is all from Group 5. Thank you.